In this session, we are going to discuss three important types of graphs which we use to represent motion. One is position time graph, the other one is velocity time graph, and the last one is acceleration time graph. We need to answer first why graphs. Graphs are especially useful in dumping a lot of information in one or two diagrams. Hence, it is very important for us to understand how to represent anything using a graph. Okay, so in our within our scope of the content, there are three types of motion you need to represent in a graph. One is rest. If you want to just talk about motion, you should know what is rest. So one is rest. The other one is uniform velocity, and the next one is non-uniform velocity. That means non-uniform motion. In non-uniform motion, we are going to talk about only uniformly accelerated motion. That is uniformly accelerated motion. So in rest, when an object is at rest, velocity is simply 0, not moving at all. There is no change in position, so velocity is 0. In uniform velocity, velocity is constant. In uniformly accelerated motion, change in velocity for every second is constant. That means acceleration is constant. These are three things which we would like to express it in the form of a graph. So what you need to understand in one thing is, there is a trigonometrical ratio. If you have a right angle triangle and if you mention this angle between these two sides is theta, then tan theta is defined as opposite side by adjacent side. This is theta's adjacent side and this is theta's opposite side. So tan theta is equal to opposite side by adjacent side. Okay, so there are three things which we would like to represent, and there are three types of graphs. One is position time graph, because whether we like it or not, whether the object moves or not, the time flows, just flows. So before getting into the nitty-gritty of whether time is a vector or scalar, we will keep those discussions later. So there are three things which you would like to represent. One is position time graph. When the position changes, velocity is taking place. So velocity time graph and acceleration time graph. These are three types of graphs here we will see. What in position time graph, how do we represent all three is what the aim of this video. One is, first, how do you represent rest? In a position time graph, you will take two axes. One is x-axis. In that x-axis, we will take time. So the time is in seconds or minutes or hours, depends on what type of motion you discuss, that you will keep. In the y-axis, what you are taking is the position. See, it's not displacement, it's position. So in this x-axis time, y-axis position. So different types of rest first. So you are having an object in your pocket. It is at rest. So 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, it's not moving anywhere and it is with you. From you, it is at 0 distance because it is with you. So how do you write that? When time 0, that means when you start observing, the object was here at 0th position. 0 means from you, it is at a position 0. After 1 second, it is still at 0 second. Then after 2 seconds, it is still with you. After 3 seconds, it is still with you. After 4 seconds, it is still with you. So this is how you represent this rest, object at rest at the origin. So what do you say? Object at rest at the origin. Because the object is with the observer itself, observer himself. Okay, then talk about something. An object is at 5 meters from you and it is there is a bag which is kept there at 5 meters from you. Then the bag is not moving at all. So how do you represent that here? This is in the y-axis we are taking position. So 1 meter, 2 meter, 3 meter, 4 meter, and here 5 meter. Then object is at 5 meter. When you start observing, object was at 5 meter. After 1 second, 5 meter. After 2 seconds, 5 meter. After 3 seconds, 5 meter. After 4 seconds, 5 meter. So any graph which is parallel to time axis represent rest in position time graph. So what about the position time graph for velocity, uniform velocity? You take x-axis time, y-axis position. So this is position, this is time, 1 2 3 4 5, and 1 second, 2 second, 3 second, 4 second, 5 seconds, and so on. This is for our convenience. I'll take 5 meters, 10 meters, 15 meters, 20 meters, etc. And right now you are having a toy. That toy can be controlled by you, and you are putting the toy down right at your foot, and you just turn it on and the toy runs. When you start observing, the toy was right at your foot. That means the toy is with the observer. That means it is at the origin. It's at the origin. And you maintain a constant speed with the toy, and the toy goes with the speed of, let us say, 5 meters per second. That means every second it covers 5 meters. Then at the end of first second it is at 5 meter. At the end of second 10 meter. At the end of third second 15 meter. At the end of fourth second 20 meter. So how do you do that? 1 second later it is at 5 meter from you. 2 seconds later 10 meter from you. 3 seconds later 15 meter from you. 4 seconds later 20 meter from you. Then it's like this. So any graph which is a straight line may be representing rest or may be representing uniform velocity in position time graph. But this straight line is parallel to time axis. This straight line is an inclined straight line. Okay, and now what you do, you put the toy down. Now adjust the speed to 2.5 meter per second. How would it run? So after 1 second it would be at 2.5 meter from you, and after 2 seconds it is at 5 meter. That means 2.5, 5, 7.5, 10, 12.5, like that. After 2 seconds 5 meter, 3 seconds 7.5, 4 seconds 10 meter, and so on. If you graph, then the graph will be still an inclined straight line, but it is slightly down, making it trying to come parallel to time axis. So if the speed increases, it is a steeper straight line, and when the speed decreases, it's a slightly less steeper one. So the steeper the straight line, then greater the velocity. So lowest velocity, and this velocity is greater than this velocity is greater. Suppose if this is object A, this is B, this is C. So C moves with greater velocity than B and A, and whereas A is moving with the velocity lesser than B and C. Then the last one is uniformly accelerated motion. So how do you represent that in a graph? If you have seen the last video, non-uniform motion, I have given one example wherein the object is at positions 5, 20, 45, and then say 60, right? So that is nothing but if you drop an object from the top of a tower, and that object will fall down, and that is attracted by the Earth's gravity. That means the object is accelerating downwards. The object is accelerating downwards because of Earth's gravitational pull. If you look at the positions of the object from the top, it is at 0 meter, after 1 second 5 meter, after 2 seconds 20 meters. That means in the first second it covers 5, in the next second it covers 15. So from 5 meter it goes 15 meters extra. It is at a position 20 meter. Then in the third second it covers 25 meters, because as it falls the speed gets increasing. So 1 second later it is at 5 meters. Suppose 5, 10, 15, 20, 25 and so on. 1 meter later 5, 2 meter 20, 3 meters 45. The graph will be like this. We call this parabola if the graph is a parabola in position time graph. This is still position, this is time. X-axis, the graduations are in seconds, in y-axis these are in meters. So if it is a straight line parallel to time axis, represents rest. So straight line, inclined straight line, that refers to uniform velocity. If it is a parabola like this, a curved one, it is acceleration. Sometimes the object get deaccelerated. That means you are going in a vehicle, you applied brakes, then it goes slowly to come to rest. Or you throw an object or anything, as it goes up, it keeps on slowing down and comes to a stop. That time, if this represents acceleration, the negative acceleration, the graph will be like this. So to summarize, in position time graph, the position time graph is also called ST graph, displacement time graph. Like rest is like this, uniform velocity is like this. If it is a greater velocity, then the line gets steeper, then the lesser velocity, line gets flatter. And in uniform acceleration, it is this, deacceleration, it is this. If it is deacceleration, it goes opposite to that. The negative thing, the negative velocity will have a line like this. Okay, what useful quantity we can get out of position time graph? Suppose there is an object going like this, or in any way you can say that. Then at a particular instant t1, if you draw a line, that will take you to the position corresponding to that. At t1, where the object is, if from t1 if you draw a line where it cuts the graph, if you take the graph to the y-axis, that means position axis, you will find the corresponding position. At time t1, the object's position is s1. Then at time t2, the object's position is s2. Now let us invoke this triangle over here. You just make it a right angle triangle. If this is s2, this is s1, this height difference will be s2 minus s1. This is what this height is s2 minus s1. This s2 minus s1 we call change in position, final position, initial position. Delta means change in position. And this side, this is t1, this is t2. This is 12 seconds, this is 5 seconds. 12 minus 5, 7 seconds. Like that, this will be t2 minus t1. This can be written as delta t. Then this angle theta. If you say this angle is theta, for this, what is tan theta? Tan theta is opposite side divided by adjacent side. Opposite side is delta S, adjacent side is delta T. This delta S by delta T, what is change in position? Displacement. What is time taken or time interval? So change in position, displacement by time interval will give you velocity. So in position time graph, if you take slope, that means tan theta, you will be able to find out the velocity of the moving object. If you look at this, in the first 1 second, velocity is less, the displacement is less. Next same 1 second, the displacement is more. The next same 1 second, the displacement is even more. That means velocity keeps on increasing. If you analyze the same in this graph, you will find the velocity keeps on decreasing. This is how we need to understand displacement time graph. One last point, in a displacement time graph, if you drop, or in a position time graph, if you take slope, that slope will give you the velocity of the object. Now let us look at velocity time graph. In velocity time graph, I'll try to put everything in one graph. Let's say this is velocity in y-axis and time in x-axis. So the time is in seconds and the velocity will be in meter per second, because velocity is displacement by time, displacement is meter, time is second, so the velocity is meter per second. So in SI system, if you put the readings, it will be in meter per second, otherwise it can be in kilometer per hour, or it can be in miles per hour. But here it can be in seconds, or it can be in hours, like that. Okay, or it can be in minutes also. if an object is at rest, velocity is 0. So velocity is 0 meter per second. This is 5 meter per second, or I'll say 10 meter per second. No, I'll say 2 meter per second, 3 meter per, 4 meter per second, 6 meter per second, 8 meters per second. If an object is at rest, its velocity is 0 meter per second. So 1 second later, 0 meter per second, 2 seconds later, 0 meter per second, 0 meter per second, and so on. So if an object is at rest, the graph is on the time axis. In velocity time graph, this graph is velocity time graph. In velocity time graph, if an object is at rest, the graph is on the time axis, because in the x-axis we have taken time. What if the object does not change its speed, it keeps on moving with the same thing? If an object is going with the speed of say 4 meter per second, then when we start observing, its velocity was 4 meter per second, 1 second later 4 meter per second, 2 seconds later 4 meter per second, because motion is uniform velocity motion, so the 4 meter per second will not change at all. Then it's a straight line. If a straight line parallel to time axis in velocity time graph, that represents uniform velocity or uniform motion. What if the velocity keeps on increasing? That means uniformly accelerated motion. Change in velocity is constant. You take a stone, you drop it on the surface of moon. The gravity on the surface of moon is roughly 2 meter per second. When you keep the object, it was at rest. 1 second later, it will become 2 meter per second. In the next 1 second, 2 meter per second will increase, so it will become 4 meter per second. In the next 1 second, it becomes 6 meter per second. In the next 1 second, 8 meter per second. So when you keep the object, you start the stop clock, then 0. After 1 second, 2 seconds, 4. So 1 second, 2 meter per second, 2 seconds, 4, 3 seconds, 6, 4 seconds, 8, 5 seconds, 10. So it's a straight line. If the graph is an inclined straight line, then this represents uniform acceleration. So in velocity time graph, if the graph is on the time axis, that represents rest. If in velocity time graph, if the graph is parallel to time axis, that refers to uniform velocity. In the velocity time graph, if the graph is an inclined straight line, that is uniformly accelerated motion. In position time graph, we found slope that happens to be velocity. Now this is velocity time graph. A graph is there. What is the quantity that we will get? Let us say this is time axis. So I am taking one time t1. So I am extending a straight line that will cut the graph at one point. I am taking that to corresponding y-axis. In the y-axis, velocity is there. At t1, the corresponding velocity is v1. At t2, the corresponding velocity is v2. Then now the same triangle I am trying to invoke it here. So this is v2, this is v1. This height will be v2 minus v1. Hence this will be v2 minus v1. So v2 minus v1 is change in velocity. This is t2 t1. So this will be t2 minus t1 or delta t. What is slope tan theta? Tan theta is opposite side by adjacent side. If this is theta, opposite side is delta v, adjacent side is delta t. So tan theta here is delta v by delta t. Delta v by delta t is nothing but acceleration. Acceleration is defined as change in velocity by time taken. So in velocity time graph, if you take slope, that slope will be equal to acceleration. So in position time graph, taking slope will give you velocity. In velocity time graph, if you take slope, that gives you acceleration. There is more to velocity time graph. In a velocity time graph, we have just found that slope of the velocity time graph gives you acceleration. What is the area of the graph? Suppose an object is moving with a constant speed v, and that velocity is v here. At time t1, you are cutting the graph, the velocity is v. After some time, at time t2, you are cutting the graph, the velocity is still v. So this area, this is a rectangular area, and this height is v because the velocity here is v. This height is v and this base is t2 t1, so it becomes t2 minus t1. t2 minus t1 is delta t. How do we define velocity? Velocity is equal to displacement by time, change in position, which is displacement by time. So the displacement is velocity into time taken. If you find area of a rectangle is base into height. Here the base is delta t, height is this velocity. So velocity into delta t is the area, but velocity into delta t is called displacement. So in velocity time graph, slope gives you acceleration, area gives you displacement. There are two important quantities we can derive out of velocity time graph. In velocity time graph, slope is acceleration, area is displacement. So this is not only true for uniform velocity, even for non-uniform velocity, for everything, the graph, the area of the graph, velocity time graph, gives you displacement. Let us look at acceleration time graph or AT graph. In AT graph, what we'll do, in the y-axis we'll take acceleration, in the x-axis the independent variable time is taken. So acceleration, change in velocity by time, velocity is in meter per second, acceleration is in second, so the unit is meter per second square. In y-axis the graduations will be in meter per second square or kilometer per hour square or miles per hour square. In x-axis the time can be in seconds or minutes or hours or like that. So here in acceleration time graph, within our scope, either velocity is 0, that is rest, velocity is constant, that is uniform velocity. If velocity is constant, change in velocity is actually 0. Only if there is change in velocity, there is acceleration. If change in velocity is 0, 0 by anything becomes 0, so acceleration is 0. If an object is moving with the same velocity, then that is on the time axis. In velocity time graph, object at rest lies on the time axis. In acceleration time graph, constant velocity, that is uniform velocity, lies on the time axis. This represents uniform velocity. What is, there is uniform acceleration, that is acceleration delta v by delta t is constant, does not change. Where and all you can experience this, you go to any planet and you drop an object, you throw an object, in all that cases acceleration is constant. Acceleration does not depend on mass. So the gravitational acceleration of Earth, Moon, any planets or even the Sun is same for all the objects gravitating towards it. In that case, acceleration is constant. When acceleration is constant, there are only two types. One is positive acceleration, the other one is negative acceleration. You're going in a car and you apply brakes and the car comes to a halt. In this case, if the braking force is constant, acceleration is constant. Here, the acceleration making the object to come to rest. That's why that is called negative acceleration or retardation or deceleration. If the acceleration is, because acceleration is defined as change in velocity by time, it is a vector quantity. Because velocity is a vector quantity, acceleration is also a vector quantity. So a positive acceleration, positive constant acceleration can be referred here like this, negative constant acceleration can be referred like this. What if you find the area? Suppose at time t1 the corresponding acceleration is a, at time t2 the corresponding acceleration is also a. Then the area of AT graph. Area of AT graph or acceleration time graph is equal to base into height. Base is t1 to t2. So this is t2 minus t1, or we can say that delta t. This delta t into the height is acceleration. So this is a into delta t. So area is base into height, base is delta t, height is a into delta t. Let us look at this thing. You cross multiply this, delta v is a into delta t. In the same fashion, area of the graph has come out to be A into delta t. A into delta t is nothing but delta v. Delta v means change in velocity. In acceleration time graph, if you find area, that will give you change in velocity. So we have seen three graphs. In position time graph, we found slope, that is velocity. In velocity time graph, we found slope, that is acceleration. In acceleration time graph, we found area, that is velocity, or change in velocity to be exact. In velocity time graph, we found area, that gives you displacement.